Looking at physics principle numeric response question scenario 2. This one's on page 10 of the booklet that I gave you on Friday in class. Talks about a sample of thorium-226 stored in a lead box. Undergoes alpha decay. Lead box has a small opening. The alpha particles go one way out the small opening, and then the daughter nucleus, whatever's left, is going to go the other way. Gets stopped by the lead box. First paragraph says, in a sample, a nucleus of thorium-226 is at rest when it undergoes alpha decay. Daughter nucleus, as we said, radium-222 has a mass and moves to the right. The thorium-226 nucleus, the radium-222 nucleus, and the alpha particle form an isolated system. So we have thorium-226 before the nucleus decays, alpha particle after the nucleus decays, and radium-222 after the nucleus decays. Now, this looks like a situation where it's almost like a person standing on ice with a ball. Guy throws the ball goes one way, person goes the other way. We analyze that situation using Pi equals Pf. Why would we not do that here? This is the same thing, right? Nucleus splits into two things, daughter nucleus, radium-222, and the alpha particle, just like the person-ball combination splits apart into the ball going one way and the person going the other way. So we know now how we're going to analyze this lead box situation. And then I'll take a look at the second paragraph to see what's going on once the alpha particle leaves the lead box. Question says, or the next paragraph says, to the left of the lead box are two parallel plates, one positively charged, the other is negatively charged. Parallel plates are 2 centimeters apart. Escaping alpha particles are stopped by the electric force just before they reach the positively charged plate. When we have a charged particle that is slowing down and stopping, that's like a car going up a hill where we say EI equals EF. So we're looking for the magnitude of the electric force here along with the two physics principles. And we know already what those physics principles are. We're going to analyze this part of it using conservation of momentum, and we're going to analyze this part of it using conservation of energy. So let's do that now. Let's do the first part, Pi equals Pf. This thorium-226 is at rest before it decays, so the initial momentum would be 0. After it decays, we have a daughter nucleus, radium-222, going to the right, and then we have an alpha particle, we'll call that mass 2, going to the left. Daughter nucleus, radium-222, has a mass, we're given that mass of 3.67 times 10 to the negative 25 kilograms times V1F. We're given that speed. We're told that it goes to the right at 3.1 times 10 to the 5 meters per second, plus M2, the mass of the alpha particle, 6.65 times 10 to the minus 27 kilograms times V2F. So we take this over by subtracting, divide by 6.65, and we're going to get a V2F, the velocity of the alpha particle, as it escapes this lead box, of negative 17108.270 meters per second. So how fast does it leave the lead box? 17108.270 meters per second. That's how fast it leaves the lead box. That's how fast it enters the parallel plates. So let's do our thing with our parallel plates. We're going to say EI equals EF. This is a car going up a hill because it's charged particles slowing down and stopping. The car at the bottom of the hill would have kinetic energy, and at the top of the hill, it would have potential energy, except it's QV potential, not MGH potential. The alpha particle has a mass of 6.65. The speed that it's moving at the bottom of the hill is the speed that it's moving after it decays. Charge of the alpha particle is 3.2. So the final potential, or the potential difference here, would be 3041262.43 volts. Now here's the thing though, we're looking in this question for the magnitude of the electric force. Electric force is Q times electric field. Electric field between two parallel plates is delta V over delta D. We just solved for the potential difference, 304.1262.43. The potential difference between the plates that we just solved for using conservation of energy. The distance between the plates, we're told, is 2 centimeters, 0.020 meters. Gives me an electric field of 1.5206 times 10 to the 8 volts per meter, which we're going to sub in here to solve for the electric force. 3.2 times 10 to the negative 19 times the field that we just found, 1.5206 times 10 to the 8 meters per second, or sorry, volts per meter. Solve that, 4.866 times 10 to the negative 11 newtons, which we're going to round to 4.9 times 10 to the negative 11 newtons. We're asked to express that A decimal B times 10 to the negative CD, 4911. Yes, they gave me an answer of 4811 here, but pretty sure that should be 4911. So let's look at what we did again. Like fundamentally, we knew two things applied here, and this is not new. Charged particle slowing down. That's what we just did. That's EI equals EF. We did some other things because we were looking to solve for the force, but fundamentally it came down to EI equals EF. And the first part of the question, where this thorium-226 was decaying, because that thorium-226 became two objects, that was like a person throwing a ball on ice. Where we have one object becoming two, we analyze it using PI equals PF. So we end up getting 4.9 times 10 to the negative 11 newtons, 4911. In our physics principles, it's pretty clear here that we used principle, what did we use here? Principle 4, conservation of momentum. We used principle 5, conservation of energy. And because we used this, we could argue that we used non-uniform motion or accelerated motion as well. The one that got us the answer, the one we did last, would be 1. Previous to that, it was 5, then 4. So we could list this as 1, 4. We could list it as 1, 5, or we could list it as 4, 5. Any combination of 1, 4, and 5. They ask us for 2 of the physics principles used. We used 3. You just need to identify 2 of the physics principles that you used.